Hi everyone, I am Dr. Anjani Devi, Associate Professor, Department of Biotechnology, Vignan's Foundation for Science, Technology and Research. As you pretty well know that I am dealing with the course Enzyme Technology and we are presently discussing about the topics in Unit 5. And in our last class, we have dealt with the basic models of your reactors. There we have studied about our batch reactors, continuous reactors. We have seen the glimpses. We have seen a overall view of the basic models of reactors. Today in this session, we will be discussing the design of immobilized enzyme reactors, specifically about packed bed reactors and fluidized bed reactors. And we will also discuss about the flow design of continuous stirred tank reactor. So, we'll start with continuous flow reactor. That's nothing but your continuous stirred tank reactor. So, in the last class, I have discussed with you what is the major difference between a batch reactor and a continuous reactor. A batch reactor is that reactor in which we are going to produce the desired product in batches, and there we are adding the substrate only once and we are removing the product from the reactor only once after completion of your reaction. But coming to the continuous stirred tank reactor, here we have a provision of continuously supplying your substrate to the enzyme which is already available in your reactor, and we can continuously remove our product of interest from the reactor at regular intervals of time. So, you can continuously add your substrate as well as you can continuously remove your product from the reactor. I'll explain you about the design of your continuous stirred tank reactor now. See, if at all you are observing the figure, you can see very clearly that it is nothing but a vessel. As I told you that the reactor is nothing but a vessel, or it is a series of vessels. So, ultimately this is a vessel which is having the space which can accommodate your substrate as well as the enzyme, as well as it will be having a tight lid, and you have a provision for your motor as well as your agitator. The motor will be fixed to your agitator so that whenever you require, you can agitate and you can go for homogeneous mixing. When you are switching on the motor, you can mix the component that is present inside your reactor so that your substrate will be homogeneously mixed and it will be continuously supplied to your enzyme available within your reactor. Moreover, your reactor will be having a jacket which will be continuously supplying either hot water or steam or cool water in order to adjust the temperature required within the reactor. So, according to your temperature requirements, you can supply either hot water or steam or cold water through the jacket. And moreover, you have baffles and you have a proper socket, or you have a proper point through which you can continuously supply your feed, which is nothing but your substrate. That is situation a case where you are going to use immobilized enzyme. So, as I have already described you, explained you what is an immobilized enzyme, we are using an enzyme, we are immobilizing that enzyme to a suitable support, and we are adding that immobilized enzyme, we are placing the immobilized enzyme within the reactor. In a continuous reactor, you are continuously supplying the substrate. Certain amount of substrate, concentration of substrate is available for the enzyme so that you can get your product. So, this is the design of your continuous flow stirred tank reactor. So, what is the advantage of this continuous flow stirred tank reactor? Why we need to use this particular sort of reactors? In the last class, we have discussed about the batch reactor. There, you can use that sort of reactors only if you want the product in very small scale. If you are working with a small scale production, you can choose the batch reactor. But if at all you want to produce your required component in a large scale, definitely you need to go for your continuous stirred tank reactor. You have to use continuous stirred tank reactor. And moreover, you can rectify the problem of contamination of your product in the case of your continuous stirred tank reactor also, as we will be using the immobilized enzyme which avoids the enzyme contamination of the product and also ensures that the average residence time of the substrate molecules in the reaction chamber is minimized to a extent possible. So, as you are continuously adding the substrate, so it is getting continuously available for your enzyme and continuous product formation is there. During the reaction that is taking place within the reactor, what is happening? There is a continuous supply of your substrate. Here you have your enzyme which is combining with your substrate in order to give rise to your product. So, there is a continuous addition of substrate and continuous removal of your product. So, there will be very less amount of time available for your substrate in order to have a proper contact with your enzyme. So, there will be minimum residence time of your substrate within the reactor. So, the principle underlying in continuous flow reactor is continuous addition of your substrate as well as continuous removal of your product from the reactor. Your stirred tank reactor will be having an inlet to add your substrate and it will be having an outlet to remove your product from the reactor. Moreover, by careful choice of the size of the reactor, by deciding the proper size of the reactor, the enzyme activity and the rate of addition of your substrate as well as the percentage conversion of your substrate to product can be adjusted to the desired extent. So, by carefully choosing the size of the tank of the reactor, you can adjust your enzyme activity as well as you can adjust the rate of addition of your substrate and the conversion of your substrate to product. So, what are the very important characters or the very important features through which you can obtain highest yield? It is nothing but low flow rate, large reactor size and high enzyme activity. If you consider these three conditions, there is a high probability of or there is a good amount of probability to acquire high yield of your product. So, what are those three conditions? You need to select the high size of your tank. Along with that, you need to go for a very low flow rate. Along with that, you need to select the enzyme with highest activity. With that, you can definitely obtain your yield at higher extent. So, in this continuous flow reactors, the immobilized enzymes may be kept inside the reactor by filtration of the stream of product by incorporating a subsequent settling stage. So, when you are placing your enzyme inside your reactor, how you can immobilize your enzyme? You can either use magnetically active particles onto which you can immobilize your enzyme. Otherwise, you can also immobilize your enzyme on the pedals of your agitator. So, you can immobilize your enzyme on the magnetically active particles and retain it in the magnetic field, as well as you can immobilize your enzyme to the pedals of the agitator. So, continuous flow stir tank reaction may be combined with the ultrafiltration process also. Why we need to combine your filtration process with the continuous stir tank reactor? In order to separate your immobilized enzyme which is in solubilized form. So, in order to separate your enzyme from your substrate, either of your enzyme or substrate, one should be in the solubilized state and other should be in the insoluble state. If both are in solubilized state, then it will be problematic for us to separate the enzyme. If at all in the reactor, if you have considered the enzyme in a solubilized state and your substrate is in unsoluble state, then you have a probability of separating your enzyme by using a combination of by attaching your ultrafiltration unit to your continuous stir tank reactor. Let us now discuss about flow reactor design equation. For continuous flow system, the time usually increases if at all you are using a increased reactor volume. If you are using a reactor of high volume, definitely the time of your reaction will be definitely increased. Here, if you see FA naught into X is equal to moles of A fed divided by the time into moles of A reacted by moles of A fed. FA naught into X, which is nothing but your molar flow rate at which A is consumed within the system. FA naught into X, which is nothing but your molar flow rate at which A is consumed by the system, is calculated as the number of moles of A fed into the system according to the time into moles of A reacted by moles of K fed into the system. So, we will be representing it as FA naught is minus FA naught into X is equal to FA. Here, FA naught is the inlet molar flow rate, whereas FA is the outlet flow rate, and FA naught into X is the molar flow rate at which your A is consumed within the system. Taking FA naught into common, FA is equal to FA naught into 1 minus X. So, FA naught is equal to CA naught into V naught. Here you need to know what is CA naught. CA naught is nothing but moles, number of moles per volume, and V naught is the volume per time, which is nothing but your volumetric flow rate, which is designated in the units of dm cube by S. For a liquid system, CA naught is usually given in terms of molarity. In liquid system, CA naught is considered in the terms of polarity, which is nothing but moles per dm cube. Whereas in the gaseous system, CA naught can be calculated using the gas law, which is nothing but CA naught is equal to PA naught divided by R into T, where P is the partial pressure, R is your gas constant, T is your temperature. So, upon substituting, you can get the entire equation as CA naught is equal to YA naught into P naught divided by R into T naught. Upon considering the entering molar flow rate, that is FA naught is equal to V naught into CA naught. If you see here, just incorporate this value in the place of CA naught. That's nothing but YA naught into P naught divided by R into T naught. So, ultimately, you will be getting V naught into YA naught into P naught divided by R into T naught. If you elaborate the term, YA naught is nothing but the entering mole fraction of A, P naught is your entering total pressure, CA naught is the entering concentration, and R is your gas constant, which is equal to 8.314 kilopascals dm cube per mole K, and T is your temperature, which is measured in terms of Kelvin. So now let us discuss about design equation of CSTR. From this reaction, we can write as V is equal to FA naught minus FA divided by minus RA. Here, upon substituting the value of FA, so what you are doing is, you are substituting the value of FA, this value here. So ultimately, after substitution, we will be getting V is equal to FA naught minus FA naught minus FA naught into X. So upon subtraction, we will be definitely getting V is equal to FA naught into X divided by minus RA. Let me elaborate the equation. V is equal to FA naught into X divided by minus RA. Here, FA naught is your molar flow rate of substrate A at the time T is equal to 0. X is your conversion, and RA is nothing but your rate of reaction. What are the advantages of your continuous tank reactor? So, what are the advantages means? It will be giving better utilization of your expensive enzymes, as you are continuously supplying your substrate to your enzyme is continuously converting the substrate into product. So, you are using your enzyme continuously. So, by this method, you can continuously use your expensive enzymes resources. Then, the amount of product formed will be higher when compared to the other batch reactors. Moreover, this continuous operation makes it easy to control the reaction conditions better. So you can control the conditions that are prevailing within the reactor comparatively better than that of the other batch reactor process. And you'll be having your improved reproducibility. Further, the substrate with a low solubility in the operating solvent may also be used in the continuous flow reactors by simply using larger volumes of their dilute solutions. Now, let us discuss about packed bed reactor. Why we are calling this reactor as packed bed reactor? Because you are packing your enzyme within the reactor. So that you can have your enzyme in a stable state. So you are packing your enzyme here, immobilized enzyme here. So immobilized enzyme is packed into the column. So here we are considering the reactor which is like a column, and we are going to pack your immobilized enzyme into the column. Let us consider that this is a column and this is your packed bed reactor. Into this, you are continuously packing your catalyst here. Your catalyst is packed in your support, and you are continuously supplying your reactants. You can either supply your reactant from the upper side or the lower side of your reactor. Let us assume that you are supplying your reactants from the lower end of your reactor, and here your reactants, which are nothing but your substrate, is entering into the system. The substrate is moving with certain amount of flow rate, and it is in contact with the enzyme now, which is already present in an immobilized state in the support. So your substrate is going and reacting with the enzyme that is present in the immobilized condition, and now the product is produced, which is separated from the upper side. Along with the product, you can also separate the unreacted components of your reactants. And if at all you want to utilize your substrate completely, recirculate your substrate once again to your enzyme, so that that remaining unreacted component of your substrate can also be get converted into your product with the action of the enzymes present immobilized in your support. So immobilized enzyme is packed into the column, and the substrate is made to flow through the column such that the product is obtained at the outlet, and the reactors like this sort is called as your packed bed reactor. The chemical reaction that takes place on the surface of your enzyme here, as I have told you that your enzyme is already present in the immobilized condition with the support. As your substrate is moving on to the enzyme, the reaction of your substrate with the enzyme is taking place on the surface of your enzyme. The advantage of this particular process is you can get a higher conversion per weight of your substrate when compared to the other catalytic reactors. So you can get more amount of your conversion, higher conversion per weight of your catalyst. And the packed bed reactors are idle when the flow rate of the packed bed reactors are idle when the flow rate profile crosses a transverse cross section of the column and is perfectly flat. The system like this are called as flux flow reactor. Let us see this. This is your flat bed reactor. If you consider the transverse cross section of this column will be perfectly flat. If you go for a transverse cross section, then your column will be absolutely flat, and this system is called as plugged flow reactor. So the flow of your substrate can enter, as I have told you that the substrate, your substrate can enter into your column either from the upper or the lower part of your column. The column can be constructed as a tall column or it may be constructed as a flat bed. And when your substrate is added through the upper part of your column, the particles of the catalyst, which is nothing but your enzyme, then tends to be jammed together, plugged in the column. This is particularly pronounced in the case of smaller particles. For example, if you consider your free enzyme or enzyme which is in small size, then definitely here there is a chance of jamming together of your enzyme and your substrate. Alternatively, what we can do, we can go for immobilizing the enzyme onto the membrane or a sheet which is available. Let us think you have taken a free enzyme within your reactor and you have supplied the substrate into your reactor. Then there is every chance that your enzyme will be in contact with your substrate, and sometimes there will be chance of formation of jam together of your enzyme and substrate. So what we are doing is we are alternatively considering the enzyme in the immobilized form. We are immobilizing our enzyme with a support or any sheet material like paper, etc. And we are confining that particular paper into the reactor and we are arranging it in a proper form and we are placing it in the reactor. A number of modifications to the packed bed reactor has occurred. As you pretty well know that if at all you are using your enzyme in the free state, there is every chance that your substrate get jammed with your enzyme. So you are considering your enzyme in immobilized form. You are making your enzyme immobilized to a proper sheet and you are placing that immobilized enzyme into the reactor. In order to achieve more amount of yield of your product, there are a number of modifications available for your packed bed reactor. One of such modification is nothing but your spiral membrane packed bed reactor. Here in the spiral membrane packed bed reactor, what is happening is we have considered a sheet. We have immobilized our enzyme and we have made the sheet in a spiral form and we have incorporated that particular immobilized enzyme into your reactor. So this is a modification to your packed bed reactor in order to increase your yield of your product. Apart from that, you can also use hollow fiber reactors. You can also use hollow fiber reactors. And the fibers that you are considering are having the diameter of your human hair. So they are very thin. The diameter of your tube is very thin. It is equal to the diameter of your human hair. So what we are doing is we are taking a series of tubes which are semi-permeable in nature. So we have considered the tubes which are semi-permeable in nature and we have immobilized our enzyme in the tube. So your immobilized means your enzyme will be in the larger size and it will be get immobilized into your tube. And you are placing your tubes inside the reactor. These are nothing but your hollow tubes. You have placed the hollow tubes into your reactor. So the tubes are made of semi-permeable material such as cellulose and these confine the larger molecules of your enzymes while allowing only the free passage of smaller molecules such as nothing but your substrate. The other modification of this packed bed reactor is nothing but your hollow fiber reactor. What is the importance of this hollow fiber reactor? We have considered a number of fibers which will be having the diameter equal to the diameter of your human hair and we have considered the series of these fibers and we are placing inside the reactor. These are nothing but your fibers. So you have incorporated a number of fibers into your reactor. What these fibers are doing and what is the importance of these fibers? We have immobilized our enzyme into this fiber and these fibers are semi-permeable. They will be allowing only the smaller particles such as substrates and products to pass through them. They will be placing the immobilized enzyme in the stable form and they will be allowing only the smaller molecular sized substrate and product. So the tubes are made up of semi-permeable material such as cellulose which confines the larger molecules that are enzyme while allowing free passage of your smaller ones which are nothing but your substrate and products. Hollow fibers are packed into the column. As I told you that we have taken that fibers and we have packed that into the column. The enzyme can be retained in the interior of the fibers. Your enzyme is available inside your hollow fibers. And once you have supplied your substrate, the substrate will be coming into the contact of this enzyme. And because of this contact, your product is produced and your product is allowed outside once again because of the smaller size of your product. So you can collect your product from the another side through your outlet. So hollow fibers are packed into the column. The enzyme can be retained into the interior of your fiber and the stream of substrate passes around the enzyme which is available in your fibers. The substrate will be diffused through the walls of the fibers. As I have told you that the fibers are semi-permeable, the reactants or the substrate will be diffusing through the walls of the fiber, reacting with the enzyme, and then once again the product is formed and that product will be diffused back through the walls of the fiber into the flow stream. Alternatively, it is possible to pass the substrate through the center of the fiber which is bathed by a solution of your enzyme. So either one method is you are supplying your substrate which is just moving into the fiber where the enzyme is present. Other method is you are directly sending your substrate into your fiber so that your substrate is bathed by a solution of your enzyme. Now let us discuss the design equation of packed bed reactor. See this figure. This is your packed bed. Your substrate molecule is entering into the reactor with a flow rate of FA0 and your product is getting released with a flow rate of FA, which is nothing but your outlet flow rate. When we consider the general mole balance equation, that is nothing but dFA divided by dW is equal to RA, and upon conversion of your flow system, FA is equal to FA0 minus FA0 into X. We know that we have discussed this conversion before. FA is equal to FA0 minus FA0 into X. The differential form of this design equation is FA0 into dx by dW, which will be equal to minus RA. The catalyst weight, which is nothing but your W, to achieve the specific conversion of X is nothing but W is equal to FA0 into dx by minus RA. Here FA is your molar flow rate of your A, and RA is nothing but your rate of reaction, and FA0 is your molar flow rate of A at initial time, that is equal to T is equal to 0, and X is your conversion. Now let us discuss about the very important key points of your packed bed reactor. The catalyst regeneration is a serious problem with this packed bed reactor. Operation is not practically isothermal. Moreover, no carryover of your catalyst particle does not require this recovery unit. So you cannot reuse your catalyst, which is nothing but your enzyme. Cannot use very small size catalyst. You need to have your catalyst in a large size. So you cannot use very small size catalyst particles due to plugging and high pressure drop. Moreover, it uses relatively large size particles for low pressure drop. And what are the various applications of this packed bed reactors? You can use this packed bed reactors for the purpose of adsorption. You can use in the ion exchange chromatographic process. You can use in distillation process, humidification process. Moreover, you can use in wastewater treatment. And now coming to the fluidized bed reactor. See, there is a prominent distinct difference between the packed bed as well as the fluidized bed reactor. In both of the cases, in the present session, we have considered the immobilized enzyme. In the packed bed reactor, the immobilized enzyme is mobilized to a support. It is in stationary form. But in the case of fluidized bed reactor, you have also considered immobilized enzyme, but it is available in free form in the mixture containing the reactants, which is nothing but your substrate. The fluidized bed reactors are a hybrid of continuous flow reactor and a packed bed reactor. So the design of this fluidized bed will be having similarities with both of these reactors, which are nothing but your continuous flow reactor as well as your packed bed reactor. the immobilized enzyme is loosely packed into the column. That I have told you that there is a prominent difference between the immobilized enzyme in case of packed bed as well as the fluidized bed. In the case of packed bed, your enzyme is in a stationary, it is tightly packed. But in the case of fluidized bed, your enzyme is immobilized very loosely. So the immobilized enzyme is loosely packed into the column and the stream of substrate is passing from the lower end to the upper part of your column at a fixed flow rate. So we have fixed the exact flow rate of your substrate, and because of this fixed flow rate, your substrate is continuously moving into your column with fixed flow rate, and you are having your immobilized enzyme within the reactor. Because of this flow, your enzyme is getting mixed with your substrate, and you know pretty well that your immobilized enzyme will be having distinct particle size and it is denser in nature. Because of this, your enzyme, immobilized enzyme, will be always available in the lower part of your column compared to the rarer enzymes. For example, if you consider your enzyme is immobilized, means it will be adding up to the weight of your enzyme. Because of its weight, it will be always present in the lower part of your column. And as I have told you that your substrate is entering into the column with certain amount of flow rate. Because of this, your enzyme is getting lift. So in this way, when the substrate is introduced into the column as a flowing stream, the bed of the solid particles is transformed into fluid-like state, making the particles of the immobilized enzyme separate and move about in the column. This column acquires the appearance of a boiling liquid. This effect is quite efficient at mixing catalyst with the substrate. According to the physical characteristics of the given immobilized enzyme system and the substrate employed in the reactor, there might be possibility of occurrence of two problems. The first problem is, as the reaction continuously that is taking place inside the reactor is exothermic, there may be increase in the temperature and there is a possibility of overheating that can take place within your reactor. And the second problem is, there might be a formation of your solvent may sometimes form a layer around the immobilized enzyme. So the second is that the large unstirred layer of the solvent may be present around the immobilized enzyme particles, resulting in inefficient mixing of the substrate and the enzyme. Let us assume that your enzyme is already immobilized, and if at all your solvent is forming a layer around your immobilized enzyme, your substrate can't get in contact with your enzyme which is in immobilized form. So there will be some mass transfer limitations. So there is a possibility of these two problems, and how you can get rectified. How can you overcome these problems means, you can overcome these by increasing the flow rate through the reactor. This will decrease the residence time in the reactor. As you are increasing the flow rate of your substrate, so the substrate is in contact with the enzyme for a little amount of time. That means your residence time of your substrate within the reactor will be prominently getting reduced because of increasing the flow rate of your substrate. So there will be decrease in the residence time in the reactor, and hence leading towards the reduction in the degree of conversion of your substrate. See, if at all your enzyme is not in proper contact with your substrate, as I have told you that in order to form the enzyme substrate complex, the enzyme should be in contact with the substrate for certain amount of time. If you are increasing the flow rate, the substrate won't be in combination with your enzyme for certain quite amount of time. So there might not be proper conversion of your substrate into your product. Thereby, because of this increased flow rate, there is every chance of reduction of your product yield. This reduction can be overcome by employing a larger reactor. By taking the larger reactor, you can rectify this problem of less time of residence. The later reduction can be overcome by employing a larger reactor, even a series of interconnected reactors. Though these are solutions which are not always economical in view of high cost of the reactor, hardware, enzymes and the polymeric support material. Alternatively, by recycling the part of stream of your product through the reactor, the efficiency or the time of residence of your substrate along with your enzyme can be increased. So, either by increasing the size of your reactor or by implementing the process of recycling, you can increase the time of contact between your substrate and enzyme so that you can get higher yield and reduce the cost and make the process economical. And now coming to the advantages of your fluidized bed reactor, you can get uniform particle mixing, you can have uniform temperature gradient, along with that the ability to operate reactors in a continuous state can be possible with the case of fluidized bed reactor. And coming to the disadvantages, what are the various disadvantages related to this fluidized bed reactor? Increased reactor vessel size is one of the problem, and pumping requirements and the pressure drop is one of the problem. Particle entrainment is one of the major problems. Lack of current understanding, erosion of internal components and pressure loss. These are the various disadvantages related with your fluidized bed reactor. And coming to the applications of fluidized bed reactor, you can use that reactor for separation of various solids, for fluid catalytic cracking, for fluidized bed combustion, heat or mass transfer or interface modifications such as applying a coating on the solid items. This technique is also important and it is becoming more common in aquaculture for the production of shellfish in integrated multi-trophic aquaculture system. So, coming to the summary, in the today's session, we have discussed about continuous stirred tank reactor and the design equation related to your continuous stirred tank reactor. Besides, we have discussed about your packed bed reactor. In that, we have also discussed about your spiral membrane packed bed reactor, hollow tube packed bed reactors, which are the advanced versions of your packed bed reactors. Besides, we have also discussed about the design equation related to your packed bed reactors. We have emphasized upon the advantages and disadvantages related to the packed bed reactors. And then we have also studied about fluidized bed reactors. Further, we have discussed about applications of fluidized bed reactors in different fields. So, please work out on these following questions in order to assess yourself that how far you have understood the today's session. I have gone through these materials in order to deliver this session. So, I want you people also to refer the same. Thank you.